start time. Are we ready? I think we got like 30 seconds to like stretch, get into it. Okay. Last time on Applied Mechanics 2, we went through some differential equations. We did a guess and check kind of method, and we ended up solving this ordinary differential equation with this x of t solution. My question to start us off is why? Why would we do that? What does that tell you? Like, why would you want to know what a solution to a differential equation is? And, yeah, go ahead if you already know. Yeah.
From the acceleration, finding the velocity and position function.
Okay, so now we have. Oh. So we have, now we know like x as a function of time, we know v as a function of time. We have both of those. We could calculate what a is as a function of time. Okay. Take a second and just kind of check in. So this is kind of the speed run of what we did, right? Identify, so we did a free body diagram. We identified MA is equal to these forces. So A plus K over MX is G. Plug in the initial conditions, and then you end up with this answer, x of t. So if we did it all in like 10 seconds, or you could just like magically, boom, this is the answer, memorized it. So why go through that effort? Is this just an exercise in math, or is this something that will fundamentally help engineering intuition or problem solving? Take a second, like just ask each other or pitch your answer. What do you think? What do we got? What do you think? This one, yeah, this one is a unique solution, right? Like it's only true for Really, I need the headset mic. It's like, but those are better. Lapel mic is like, I don't know, it's professional. It looks fun. Okay, so what do we think? Why go through this math exercise? Did anyone come up with like a reason? Some said like, well, calculus is fun, so why not just do the calculus? Yeah. Can always, and we can just make the differential equation even more complicated. We can add extra like like x dots and put a time function over on the right hand side. We can do all sorts of stuff, but why would we do that? As an engineer who's like looking for answers and actionable insights, what does a solution to a differential equation do? So one thing that came up was like we went from kind of a general function of functions of like acceleration plus position has to be constant, and that it doesn't really tell us anything of like, well, what happened at 2 seconds? Like, well, I don't know, maybe this. It's a general truism versus this equation up here. If someone says what happens at 2 seconds, we can plug in a 2 and get exactly this is position at 2 seconds. We can take a derivative and we can get this is velocity at exactly 2 seconds, something like that. So that could be helpful, or is that not helpful? It sounded helpful. Yeah, like now we have like a real function that we can evaluate. Anything else? Any thoughts? No? Keep them to yourself. It's always better to just like hide your thoughts. That way no one can judge them. No, opposite. Share. You have a thought or no?
Sure.
Yeah.
You can take limit as t goes to infinity to see if it will ever stop or if it will approach some value.
Okay.
For
Yeah.
Position or time, velocity or acceleration.
We have a function, we can start looking at like what's happening. Here it's like an actual evaluate, like a function of t. We could plug in t is infinity and figure out, oh, as t goes to infinity, it's just gonna keep bouncing because it's still a sine and a cosine. Yeah, so we can start doing like limits. So we have like some actual insight into what happens when this thing hits the spring. Which, nobody said this, but let's see, do I have the right one? W squared, I think. We could actually plot, like, hey, it starts, oh, I don't think that's right. I think like this. That looks a little better to me, right? G over omega squared, G over omega squared. I think those are the terms that we had, right? So what's happening here? We have like x of t plotted versus time. Oh, and I plotted the negative. Let's go regular. So in terms of like, what is x of t? We can say, all right, the more it presses in, the bigger that number gets, the more I'm like compressing that spring. Anything from this graph? Does this graph help us at all? It's wavy. Goes up and down.
And it gives a good representation of the position over time on the spring, but I don't think it's entirely realistic.
Oh, it doesn't feel realistic? Okay.
Like, why is it oscillating so much in 1 second? I feel like if you drop the weight on a spring, it's gonna bounce off.
Okay. Yeah, yeah.
Also, it's oscillating like the same amount every time when it moves energy over time. So like the y axis would like get smaller on each.
So you think this should be like decaying?
Yeah,
Okay.
I think so.
Yep.
I have a small question. Why is it X and T instead of like Y and T? It's like going up.
If it's going up and down, that one,
Or is it just like a distance? Or are you just trying to say like the distance increases? Because, oh no, it isn't.
no, and that one is just like my own labeling. I just chose X as up and down and Y as left and right. Not a particular reason for it. Just take the axis and instead of up and down, rotate it by 90 degrees. So we could have called it Y, and it'd be the same kind of function, right? So how would we get the amplitude to decrease like that? Yeah.
Well, we could take energy out of the system.
Okay, what would take energy out? I mean, we can't like create and destroy energy, but like we can at least convert energy. One thing we can do, at least for dynamics and not really care about it, is like convert mechanical energy into heat, and then it's no longer part of our system. Yeah.
As I said, the spring won't be lossless, presumably, as it flexes and heat, it'll slowly lose this ability.
Okay. Yeah. Yeah. So there will be some losses in the spring. But that would come back to here. Right now we said we have a spring, it's linear elastic, we have a mass, and then we have gravity. So at least in terms of our free body diagram, the solution that we have makes sense for describing these forces. At least I think it makes sense. Maybe you also, maybe you think like, no, there should be something else, but it at least solves, it creates a differential equation, we can solve it, we get the answer. The answer is doing what it's supposed to do, it's solving that diffie Q. Too quiet today. What force would you add if you want it to decrease? You want amplitude to get out. You want it to change. What is it? Drag. Okay. Drag through the air. Do we think that would be the main? We're only doing, sorry. A normal force counter normal force? A normal force. I don't know. Give it it a shot. Like what? Yeah, take a second. What would you add to this free body diagram if you really want to add the fact that this amplitude should decrease? What would be a force that would decrease that amplitude? Just take a second. You can try to add it. You can always say it equals 0 in the ideal case, but what would it look like on your free body diagram? So one thing that came up was kind of like when we go down and then come back up, really when we get to here, it should be like a free fall equation, and then it should hit again and do the same thing. We did not include that in our free body diagram. We didn't say that X is only valid from like whatever. There's only positive X spring forces, and then everything below zero is something else. That would be a different solution. So we solve for the simplified case that when the thing hits the spring, it just sticks to it, and it's just going to bounce up and down from there. That's what we solved for. And again, whether or not that's helpful, it's like, well, that's ridiculous. That's not real. And even if we don't think it's real, everything from here to here, that's real. Like while it's compressing and while it's coming back up, all that's true. So at least we did something, right? Maybe we just want to zoom in on that quick 0.1 seconds. Let's go 1.5. So maybe it goes up and then down, and then something happens after that. And it's outside the scope of our little like diagram. Then another thought came up of like, what's the deal? Why is it vibrating so fast? Like, what is happening there? What are the things that affect that vibration? Like if we wanted to vibrate slower, we want less, what would we have to change? Yeah. Internal force on the spring? How would we change that, like internal force? What could we do? Okay, yeah. So like something about the spring itself would be different, right? All right, I like that idea. More stiffness? Or less? But something. Stiffness? You think, gotta change the stiffness. Stiffer spring, what do you think? More vibrations or less vibrations? I heard both. I heard less and more. We could try it. You want to try it? Let's see what happens. So what do you want to do? Make K bigger or smaller? Smaller. We'll make it smaller. And let's go back to like 1 second. Make it half. Make it 50. And it's back to 1 second. So two things happened. One, amplitude increased a little bit because we're talking about like an impact, like a velocity hitting this thing. Other thing is that it slowed down. So the more compliant your spring, the lower, because there's two parts to that. This is called the natural frequency, omega. So the system with no other outside forces, it's going to oscillate in this frequency. So that's the natural frequency. So we can decrease stiffness or we can increase mass. Both of them will decrease natural frequency of the system. It doesn't change like damping. It doesn't change. It's still going to oscillate forever, at least in our simple model. But it does change how often it's oscillating.
Does this equation support if we say limit the length of the spring to less than the stopping distance? So like we only want to
Yeah.
slow the block until the block makes impact.
All right. Alright, so let's put this back to our initial, or I guess we'll come back here. And then I'll come back to the question, to my original question of like, how do we damp it? So even just looking at that first kind of curve up and back down, the question was like, if we only have a spring that, like right now it says 0.1, so 10 centimeters, so a 10 centimeter deflection. If we only had a 5 centimeter spring, is this still valid? Would the same thing happen? Is it still a linear spring if you compress it to the point where it's like interfering with itself? What happens is it becomes a nonlinear spring. So general kind of linear spring is like you have a slope that is K. As it starts to interfere with itself, there will be some kind of transition where it's getting stiffer. And then it gets super stiff because now you're compressing steel. Like you're just smushing a steel tube into itself. So now it's probably around 200 gigapascal modulus times whatever the cross-sectional area of that spring is. So it gets real stiff real quick. So we would, usually what happens is you figure out how much the spring is going to deflect, and you make the spring at least that long and probably longer so that it's actually a linear spring rather than having damage to your spring every time you use it. So you end up with two different spring constants. So one thought people had was like, what if we added friction, like some kind of friction parameter in there? Friction would definitely like decrease, because it's taking kinetic energy and turning that into heat somehow. So that would help. We would have it would be a different set of equations. Like we would need to go back and resolve that differential equation, but that would be one way to say. Friction's kind of weird because you end up with like a straight line. Like it's not an exponential decay, it's a linear decay of the amplitude, which is kind of cool. It's also kind of annoying to solve like an actual function for it because you have to keep plugging in a new initial condition every time you switch directions. Yeah.
How would that work? Is you subtract a multiplication because it switches direction depending on the right?
Yeah, it does. So the friction does switch directions because as we're moving down, friction's moving up. But then as we bounce back up, friction's moving down, even though our force of friction is just some constant, mu times that normal force. And yeah, one way is like take absolute value of the speed, and So we could say mu n times v over v. So we always get a 1 or a -1, whether we're moving up or down, and then we would flip the direction of that friction that way. Again, that one's a little annoying. It turns the linear ODE into a non-linear. Well, I guess it's still a linear ODE, but you have to keep switching the direction of before, so you have to solve lots of linear ODEs. Okay. So so I asked a question, then we came up with some other questions. Where are we at now? Not sure. We beat it to death. So I could just move on. How much time? We got time. All right, let's try something different. Move on to part B. Because here, like we have an answer. You can do stuff with it. What you want to do with that answer is up to you. But let's take a look at B. So we had, we have this equation, or at least we have this free body diagram, and I'm just kind of like simplifying the work into just bare minimum. What is the equation of motion from this free body diagram and kinetic diagram? That's where we'll start in the same spot and then we'll go from there. So what's the equation of motion? No, probably not. Because it's more, that's an engineering So I've seen this in a couple of different versions. NG minus BV. What's on my left-hand side? Mass times acceleration. To me, like going from like drawing a good free body diagram and getting to the equation of motion, like that's it. Like that's what you need to be able to do in this class. From there, like solving them, it helps to give you some intuition of like which forces you want to include, but there's tons of different ways to approach solving differential equations. And this is not a differential equations class. It's just we're always going to end up with equations of motion that are differential equations. So it's good to know some of the solutions, but you don't need to be like an expert in ODEs and math and calculus and all that. This is the most important part. Free body diagram, what are the forces, and then what is the equation of motion? Now we'll do some fun math because we love math. That's just who we are. That's why we're here. It's the essence of the engineer. So kind of I'm going through the same process that we did with a spring, right? Take all the derivatives, put them on one side, and then the stuff that's not a derivative, put it over on the other side. Very similar equation to what we did with the spring, but it's a little different. We don't have any position here, only acceleration and velocity. We have an MA term and we have a B times V term. With the spring, we split it up into two sets of equations, that homogeneous and that particular solution. Does this ring a bell? What did I do?
XP is particular, right?
XP is particular, yeah.
And the homogeneous equation.
What did I draw?
You said equals 0, that was particular.
Oh, whoops. I didn't mean to write equals anything. All right, thanks. Yeah. Okay, they're both equal to something. I didn't mean to write a 0 there. It's not 0, which I'm glad you pointed out. One of them, what's the homogeneous equal to? Add those two up. That's our 0. That's also called like the natural solution, like what happens when there are no external forces on it. And then particular would be that forced solution. Like what does the system do when, like, under this force, like when something's on it? So what is that second part equal to? What? It is dusty. What is the second part? Yeah.
Isn't it gravity?
Just G. Yeah. I didn't do anything here. I'm just saying 0 plus G has to equal G. But I'm saying that I can solve those two separate equations. And really what I'm doing is just trying to set you up so that you can try it. So what do you think? We have a double dot and a dot equals 0, and then we have a double dot and a dot equals a constant. What kind of functions do we need? What are we doing with these? Something? A power? E to the something? I like e to the something. Yeah. E to the x. E to the mx. What do we think about that one? Negative mx? Okay. That's a good like intuition. Like, gotta, it's not gonna ex, it's gonna like ex. Yeah.
So why keep going? I think the reason why this argument was
All right, we are out of time, so this was the guess. This was one guess for like that homogeneous. It'll be some kind of e to the negative mt. How does that sound? It'll decay, something like that. So always like add like some kind of integration constant, and then to be continued. We'll pick it up where we left off. See you on Friday. Thanks.